Hi, and welcome to another Hopper 6502 assembly video. This video is in two parts. The first one is going to be an illustration of how you would use the Hopper 6502 toolchain to write assembly code and get it into a ROM and get it running on your device. The second part of the video is going to be a little bit of a discussion of the extra bit instructions, zero-page bit instructions on the Western design version of the 6502 and their merits. So let's get started. Okay, there are other videos in this playlist about writing the Hopper minimal runtime that's this here. So it's to get the Hopper stack machine running on this 6502 machine. You don't have to do that though. You don't have to be coding in Hopper. You can be coding directly in 6502 assembly. So what I've got to open up here is the Hopper development environment. And the Hopper development environment supports both Hopper code and assembly code. So if you look in the top right, it's .asm for assembly. So the Hopper IDE knows this is assembly and not Hopper code, but a lot of the sort of curly brace and semicolon familiarity of Hopper exists in Hopper assembly as well. So these things look like methods. They just don't have arguments or return values, because in assembly you can do that any way you like, usually in registers or on the stack. By default, the entry is Hopper, so the restart vector goes to Hopper, and then the other two vectors are NMI and IRQ, and you don't have to include them, and they won't be in your it won't put them in the ROM, but if you do include them, they automatically go to these two methods. I'm taking advantage of the runtime library I wrote for the Hopper minimal runtime to use that from assembly as well. So I'm taking advantage, well, I have to. I've got the 6850 here, the Motorola serial port that's going via my FTDI. The power's coming from FTDI as well. And I've also got the Western Design Center via here, the versatile interface adapter. So because I've got them set up to do interrupts, that's via that diode there, I should initialize them, otherwise they'll just do wild things with the interrupts. And I should have interrupt service routines for them. So this is the sort of minimal setup here is to include serial, include the VIA, and have their service routines set up and initialize them. That's pretty much all you have to do. Well, if you're using my hardware, I've sent off to build a PCB, and soon anybody will be able to build this board. Right, so I'm going to illustrate how I've used them. I'm blinking an LED, as you can see, on the VIA on port B7, so the highest pin there. I'm illustrating how to use the delay, which uses the timer on the VIA. I'm doing a 500 millisecond delay here using the Hopper runtime delay method. If I right click on here, it'll take me to the definition. So this is how it works. So let's go and have a look. If I control backspace, I go back. So it's really nice to work in the Hopper IDE. If we go and look at what happens in the interrupt service routine for time, right click on this one, it just increments a 32-bit tick count. And it's been initialized based on the clock speed. So depending on if it's 8 megahertz, 4 megahertz, 1 megahertz, etc., it's been initialized so that it will update this tick every 1,000 microseconds, so every 1 millisecond. And then the let's go back again, control backspace. The delay makes a snapshot. When you come into delay, it takes your delay, which is in a 0-page variable called top L and top H for least and most significant bytes of a 16-bit uint, and it creates a target value, a 32-bit target value, with the top 2 bytes being 0. Not being 0, the top 2 bytes of your desired time delay being 0. So it takes your time delay, adds it to the current tick count that's currently in the that the timer is currently on, and it creates a target, and then it'll loop and wait for the target to be greater than or equal to the ticks. Greater than or equal to, because you might miss a tick, and you don't want to hang. So that's how the delay works. And I've made some changes so that you don't have to use the Hopper runtime stack. You can just put your arguments straight into top, and then the results from the delay API or seconds API will tell you. It looks at the current 32-bit tick, divides by 1,000 to get seconds because the tick is in milliseconds. So it's using the runtime library's long division. So divide. Anyway, it's got a 32-bit division algorithm implemented, and then again, it doesn't put it on the stack. It just puts the results back in that 0-page variable. The use of the 0-page, let's see if I can get there quickly here. Yeah, so this is how the 0-page is mapped and used by Hopper, the various different things it uses the 0-page for. And I've also got it documented in this Google spreadsheet as to how Hopper uses the 0-page. And I'll come back to that later when I talk about the bit instructions. Right. Anyhow, how's about we burn this onto the ROM? So how would I do this? So I've written my Hopper code. It's got, my assembly code. It's got structured programming constructs that you'd expect to see in a high level language, but these are implemented in assembly. So like an if else, for example, and it will automatically do the correct conditional branches here, and then the optimizer will automatically make them short or long branches depending on what's possible. Like if you try and do a conditional long branch, it'll swap that for 2 branches. So invert the condition and do a short branch and then a long branch to deal with that. So the optimizer does all this for you. 6502 assembly optimizer. So if I press F7 to build, all the commands are on the menus with their shortcuts, and their Visual Studio shortcuts. So, the default ones. So they built it, assembled it, and I've now got an Intel hex file here to put onto my ROM. So let's go do that. So let's turn the power off. Let's get the ROM out of there. Put it into my EEPROM programmer. And go to my EEPROM programmer burner. Actually, you probably want to see that. So there it is, blink. And I'm going to tell it that this ROM address starts at 8000 hex, and I'm going to burn zeros in so that you can see what it's burning. So let's load that up. So at the end of the EEPROM, these are the vectors. So the NMI, the IRQ, and the restart vectors. And then the rest of it's filled with zeros, except for it starts over here, and that's where our code is. Okay, let's program our ROM. And it is programming it. And verifying it, and it's all happy. So in theory, we should have a working ROM here. Let's put that back in, make sure it's the right way around. And turn the power on again. And we have blinking happening. And I've got another console open here. So in this one, let's load up the Hopper terminal. in the Hopper environment. It's got that FTDI as pretending to be a COM port. And what we're seeing here is the hex increment in seconds, because another thing I'm demonstrating here is the use of the serial port, using the Hopper runtime library, but using it just from regular assembler, not from Hopper. Another thing I did here is I made the non-maskable interrupt reset the timer. So if I go and press the non-maskable interrupt, then over here it returned to 0 and started again. And it's counting twice for every second. Why is it doing that? Well, it's because my delay is 500 milliseconds, so half a second. So every half a second, it's doing a half a second delay, and then every half a second it's fetching the time and then outputting it as hex to the serial port and an end of line right after the serial port. Anyway, so there you have it. That's the first half of the demo done. This shows you how you can use the Hopper development environment to write 6502 assembly and burn it to your EEPROM and get it onto your device. And to configure it to work on your device, most of what you need to configure you'll find in these two files, in the 0-page file. So how have you set up your 0-page? And you can change these addresses to, like if your VIA is not on the 0-page like mine is, you can put full addresses in here. It's 16-bit addresses. And the same is true of serial. So it's got a memory map as well. So, what's the memory map? So this is really the Hopper memory map. So it's not really all relevant to what you're coding in assembly. But to make the two live in harmony together, it's probably good not to stomp on them. Like, for example, I'm using the serial APIs from the Hopper APIs, and they have a buffer. So if I right-click on these and go and look at the buffer in and out pointer on the 0-page, the buffer itself, if I right-click on, where's the buffer? There's the, where can I find the buffer? In the ISR probably. No, where it writes to the buffer. Where is it writing or reading from the buffer? Here we go, there's the buffer. And the buffer is address serial buffer, so that's in the memory map. So let's go have a look at that. It's on page 2 of the memory of the 6502. So from, actually that comment is incorrect. So that comment should be 2. Here we go. Fix the comments. So that's where the serial buffer is. So it makes sense if you want to use and take advantage of the APIs that I've written for the firmware for the Hopper environment. It makes sense not to respect the Hopper environment's memory map and 0-page as much as possible. All right, let's get to the second part of this demo. So the original 6502, the MOS 6502, has a smaller instruction set, and it's a perfectly capable instruction set. But when the Western Design Center one with the S on the end here added a whole bunch of instructions, and they're also in the Rockwell version, except that the stop and wait instructions are not there. So here's the Rockwell instruction set. It's just got 2 less instructions. But let's stick with the Western Design one, for example. And most of my code in my runtime library, there's a define here to say which one you're using. So if you go and look at, say, the initialization, there's a lot of if-defs to say use the more compact instructions if they exist. So one of the nicer instructions with the Western Design is the store 0 instruction, this one here. So you can store 0 to an absolute address and index into the 0-page or to the 0-page. This is kind of handy because it's quite something you do quite often. Is 0 is quite a common thing we use in code. So you can save yourself a couple of bytes here and there if you use that store 0 instruction. It also has pushing and popping of the X and Y register, whereas the original doesn't. So the original can just push and pop the flags and push and pop A. But being able to push and pop the Y register and the X register are kind of handy as well, so that you don't have to do any gymnastics to use the, move them into the accumulator to do it. All right, so I'm going to demonstrate a place where I used, yeah, it's a good example. So the blink, so what I'm doing here, blinking. So to be able to use these extra instructions, what do they do, right? So there's some instructions here, the reset, there's 8 reset instructions and 8 set instructions. And then there's 8 branch if reset and 8 branch if set instructions, right? And these work on the 0 page. So let's look at the set instruction. So this will set bit 0 in the specified 0 page location. And the key part is it does not affect any flags or registers. And that is true of all 16 of these instructions. They do not affect any flags or registers, right? But they do only work on the 0 page. They're also only 2 bytes long because they have the 0 page address and the instruction name. So they're all only 2 bytes long. So they all only take a 0 page address, and that's it as a second argument. Right, so let's see what we can do with them. So I'm using them to blink this LED. So the LED, like I said, is on PB7, so port B bit 7. And I've kind of got it blinking in the inverse. So I've got the cathode on the exit to the port, and I've got it plugged into the positive rail there. So inverted. Anyway, doesn't matter, it's just blinking. So this instruction here, if the bit is set, if 7 is set on that address, then reset it. In other words, make it 0. Otherwise, set it. So that's alternating, right? What is this? Let's right click on that. So my via port is on the 0 page from hex F0 to hex FE. Actually, it's FF. There's a 16th register I'm not showing. And my Motorola is on EC and ED. EE and EF are also addressed. I do my addressing using a CPLD over here, and I map those to the VIA as well, because if you're using if you're using like the Western Design or the Rockwell VIA, not VIA, ACIA, if you're using their ACIA, you need 4 addresses. If you're using the Motorola, you only need 2 addresses, and it shares 2 registers between control and status, because the ones are read-only, and so this is a write-only register and this is a read-only register, so they can share the same addresses. So let's look again at my 0 page. So this bottom row here, let's see if I can do that. Yeah, so this bottom row here is F0 to F, and it's mapped to the VIA, and then these 4 addresses here are mapped to the serial port, the ACIA. And because I'm doing my address decoding with a CPLD, I'm not wasting a single byte. So there are no wasted bytes. These chips are only mapped to these address ranges. And I've been doing this for a while. My original map is slightly different. That was my original first version last year, but I mapped the ports the same way. So that's how they mapped into the 0 page. Let's go back to the code. Control backspace. You can right click on things to go to them in this Hopper environment. It's a really great way of navigating your project, and your project is basically defined by the user's statements. So you can navigate your source. You can right click on these as well. And so the assembler knows which source code to use for your project, just simply based on the structure of the user statements in your source. So you don't actually have to build any kind of make file or project or that sort of thing. There's no include statements. They kind of double for the include statements. All right, back to the code. So that code there. So let's write that code as if we didn't have these instructions. So you could do like bit 0 port port B, and then you could go if minus, then do the one thing, and otherwise do the other thing. But since we're about to write the portal every single time, we might as well load that port like that. And once we've loaded it again, minus is a popular trick. You can either check for minus or for overflow, because we've got branch instructions on minus or overflow. So there's minus. So it'll check the first bit, so whether this end flag is set or not, and then overflow will check the second bit. So it's a popular trick to bits 7 and 6 are more valuable than other bits simply because you can do a branch instruction on them without doing a compare. Okay, so in this case we want to turn it off, and we've loaded it into the accumulators, so we'll probably exclusive OR it. To turn it off, we'll exclusive OR it with the balance of the bits. And the syntax for in the Hopper assembler is similar to C or C#. So my format for hex and for binary and the way you do expressions, it looks like C. So if you're continually switching between the two different languages, it's very comfortable. So that's what we're going to do to we want to AND it with, to turn it off. We could exclusive OR it, or we could just AND it. So that would turn it off. So if it's set, that would, because minus flag, the first bit is set, that ANDs it, that turns it off. And then to turn it on, we just OR the register with just with the bits, and it's so B binary 1, 1, 2, 3, 4, 5, 6, 7. There we go. And then when we're done with both of those, we can just store it back to 0 page port B, like that, right? So let's see if that works. Let's see if that's going to blink our LED the same way it should. Build it. Let's go and take the power out. Switch back to the screen. Pop out our chip. Burn the chip. Program. Okay, our chip is programmed. I'm going to put it back. And turn the power back on. And we're not blinking. I don't like that we're not blinking. I was hoping we'd be blinking. Oh, it is sort of blinking. Can you see that? There's a little flash going on there. What is wrong with my code? Now it's working. Did it have a loose connection? I think it might have had a loose connection on my power. The power is a little bit wobbly here. See that? So let's reset it. Yeah, okay, it's working fine. I've had that happen earlier today with the power. And then, yeah. Okay, so I'm blinking the same way. So same code. But let's go back to the code again and have a closer look at it. Right? Strictly speaking, these are not the same. Okay, because like I said, these bit instructions above, they don't, you've got to learn a New Zealand word. The word munted. To munt something is to mess it up. So these instructions do not munt the A register. These instructions below do mount the A register. So we'd actually, to make them equivalent, we'd have to push and pop the A register, right? There's another thing. These instructions do not mount the flags. So I would have to push and pop the flags as well. So push and pop processor state like that. So now these are equivalent. So this code is equivalent to this code. So let's build it. And let's go and have a look at that. So if I go, I think I've got it in my history here. Yeah, the edit the listing. Right at the top conveniently is the Hopper. So this is the assembly listing generated by the disassembler for the Hopper assembler. Again, the syntax here is in my C/C# syntax. If you don't like that, you could do a 6.5 DASM, it's called Blink, and you can do an OG format. So if you're one of the OGs who doesn't like my syntax, now the syntax doesn't have 0x for hex, and it has a $sign for hex here, and it has semicolons instead of slashes for comments. So yes, if you are an OG and you don't like my syntax, you can see the old syntax, and that works in the emulator as well. For when you're debugging, you can see the old syntax that way too. All right, let's have a look at the code that was generated by the optimizing assembler. So the code for the bit instructions is there, and the code here is for the regular if. So here's an interesting thing to see what the assembler does. I said if minus, right? And what that really means is if plus, skip this section. And that's what the optimizing assembler did. It just says, if it was plus, branch past it to here. And then there's another branch in here to get out of there. And it uses short and long branches. It uses short branches where it can. Like, for example, this branch instruction does not exist on the MOS, the original version of the 6502. It doesn't have an unconditional branch. People do a trick there where they, if they know the state of a certain flag, they can use one of the conditional branches instead of to get a short branch. But that's a 2-byte branch. So strictly speaking, if you were using the MOS only instructions, this would be 3 bytes, not 2 bytes. The unconditional branch. But let's count up some bytes. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bytes. Strictly speaking, 17, because this would have to be a long branch. But 16, let's give it 16. The short version with the bit instructions, where it doesn't stomp on the A register, doesn't stomp on the flags, which cost us 4 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes. So it's almost double the size. So in terms of code density, you get a significant advantage if you use these bit instructions and if you map key parts of your system to the 0 page and take advantage of them. I suspect there's also a cycles advantage. We should have a look. So how many cycles does this take? 5 plus 1 or plus 2 here. Let's switch to the wrong screen. Sorry, there you go. So the branch instruction takes somewhere between 5 and 7 cycles, the branch 0. Right. Obviously, more instructions are going to take longer, but let's see what the regular branch instructions, they're probably similar. So like branch minus, for example. No, it's quicker. It's 2. Because it doesn't go and fetch that value, from the 0 page. Yeah, so 2 plus or minus 1. So you probably find there's not actually, so the number of cycles, if you add the load plus the branch together, you probably get the same number of cycles as just this instruction. Let's go have a look at these ones. So they're always 5 cycles, the resets and sets, and that would be the same as the load and store to the 0 page. Here would be, that's only 3 cycles, 0 page load. Yeah, but you can't just do a 0 page load. You would have had to have done an or and an and. So yeah, so these instructions, they chew a lot of cycles by the look of it. I mean, these ones, the bit instructions chew a lot of cycles. But so do multiple instructions if you use 3 instructions instead of 1. So you probably find in terms of timing, it's a wash between the bit instructions and the and not using the bit instructions. But in terms of code density, if you use this stuff a lot, you get quite a big benefit. So let's go have another look, one more look at another way I use these instructions. So that's in my interrupt service routines. Now, in an interrupt service routine, speed matters, but also it helps if you don't stomp on the A register, for example. The interrupt, I believe, stores and restores the process state, so it stores and restores flags, but it doesn't store and restore the A register, for example. So if we go in here and we check out the interrupt service routine, what are we in for the serial chip? I'm using one of the bit instructions to check whether there is a request, and then I'm using one to see if there's a character waiting. And if there is, then I go into a bit of code where I need to push and pop registers, and I need to update. I need to read in that byte from the serial port, decide whether it's Control C or not, which I do something special with, and if not, put it into the buffer. But in the vast majority of times that execution will come through this service routine, it just checks the 2-bit instructions, and that's if it's running on the Western Design Center chip. If it's running on the original MOS instruction set, then it has to push and pop so that it can use the A register, right? I guess I could have used bit here. Could have used bit on the bit instruction on the status register. So yeah, I could have got away with it without doing a push and pop here. Just use the bit instruction on the status register. But as soon as I got through to the next level, I wouldn't have been able to use the bit instruction. The bit instruction is kind of handy because it checks the it checks the bit 7 and bit 6 without modifying anything except the flag. So it doesn't modify against a memory address. So you can check the bit instruction, you can check against a 0-page address, and it'll set or not set the top 2 flags. So it's a common. That's why it's kind of important that top bit in 0-page bytes is very handy, because you can just check it with a single instruction. So I could have moved my push further down here, and only when there is an interrupt would it taken up a bit more. So let's go have a look at the other one. This is the buyer's interrupt handler. So same story. Oh, look, I do use the bit instruction here. So exactly what I was talking about. So that and it looks like with the VIA, it's in whether it was a timer interrupt for timer 1 is in bit 6. So I can check bit 7 with the minus, if minus, and I can check if overflow to check. Let's show you again. So I've got those top 2 flags set. So I can use the minus flag to check for bit 7 and the overflow flag to check for bit 6. And then I use the bit instruction again because the bit instruction reads. That's how it reads that memory address. So, and that's how you clear the interrupt flag on the timer. And then increment the tick counts. So this doesn't touch any registers. It mounts the 0 flag, but the interrupt service routine will restore that because it stores and restores the process state. Anyway, I think this is clearer in terms of what's going on in the code, whereas using these flags is sort of hidden trickery. If you don't know, if you're not familiar with the trick, you can't really see why the hell this works. Whereas this is obvious. It's like bit 7 and bit 6. Are they set or not set? Yeah. All right. There you go. Why I like these instructions. So I have written the Hopper runtime so that it'll run on all the chips. I test with the Rockwell chip, with the Western Design Center chip, and with the original MOS version of the chip. Yeah, there we go. Anyhow, thank you for watching this video on how you use the Hopper assembly toolchain. there are other videos on the playlists which show you how to get the Hopper environment set up on a Windows machine so that you can start using it. Yeah, go ahead and watch those. And then I'm busy. I redid this design of my single board computer, which is based on lots of other people's designs, including Grant Searle's and Ben Eater's and Garth Wilson's. And I've tried to make a minimal design which has important features for experimenting with, developing code for 6502s. So RAM and ROM, serial ports, a parallel port. The main reason it's got the parallel port is because I wanted the timer. And then it's got an NMI, which does a reset of the timer, and it's got a reset that resets the CPU. I've got separate crystals for the CPU and the serial port, which, yeah, you don't need two crystals. You could put a divider in or something, or run your CPU at a different speed. But I wanted to max out the CPU speed, which is about 8 megahertz, and it's constrained not by, the WC chip can go to 14 megahertz, I believe, but the RAM chips that are popularly available pretty much top out at about 8 megahertz, so that's how constrained. And the CPLD, and on my circuit board, my design is such that I support multiple different CPLDs, so I've tested this address decoding on 2 different versions of the, I think it's 28-pin CPLD. Or is that 24-pin? 24-pin CPLD. So that I'm hoping it can be, and I've also tested, you can use the 8K ROM or a 32K ROM, which the 8K ROM is easier to get hold of nowadays, and the Hopper runtime fits in 8K. And this here is, if I build it right now, let's see how big it is. If I run the disassembler again. So that's just over 400 bytes of code. So it certainly fits within an 8K ROM. And that includes the most useful parts of the runtime library for these devices. So it includes the serial port I/O, and it includes a break key, so that you can hook up the NMI to be a break key if you like, and it includes the timer functionality. Yeah, that's about it. So yeah, only 400 bytes. So you could run this on a much smaller ROM. What else is interchangeable? Oh, in the board I've made it so that I decided to use CAN crystals. CAN oscillators, they're simpler. But I also designed the board so that you can have either have a DIP 14 or a DIP 8 size crystal, and it'll still work on my board. So I'm hoping my board is relatively generic. Yeah, I'll do another video on that when it arrives. Alrighty, thank you for watching. Enjoy the rest of the 6502 playlist.